So this is the example we just solved. This is the book solution. Same kind of graph. We did the same kind of solution just so you can see it. Follow it with a little more explanation. So if you want to pause and look through this solution again, if that's clearer to you, then be my guest. So we just looked at the definition of current, and now we're going to look at the definition of voltage and some bits about power. So for this one, you can see here the equation VAB equals dW over dQ. So VAB is saying the voltage potential at these two individual points, at point A and point B, equals dW over dQ. dW is the potential to do work, and dQ is the charge potential. So essentially the units for this one are going to be volts are in volts, of course, as the unit. And then dW is a joule, and then dQ, like we talked about, and the last one is coulomb. So remember, joule is the unit of work, essentially, that we're using. So you can think of voltage, the voltage potential, again, to go back to the water analogy, as the pressure of water being held up, as the push of water coming down. So if you look at the picture on the left, you have the height between the two. You're looking at what is the pressure difference, essentially, from point A to point B. So obviously the water at the very top only has air pushing on it. So that's going to be much, much less pressure than at point B, where you have that entire height of water pushing down on it. So the pressure at point B is going to be much, much greater than the pressure at point A. There's more push happening. So with that, we're going to look right underneath it to the circuit analogy. At point A, you're going to have you're having negative electrons coming down around to point B, so you're going to have a greater potential at one of the points A or B as charge moves from A and B. So if we go back over a little bit more to here, the circuit that we're looking at from A to B in the center, which is 12 volts, is going to be the exact same as going in the opposite direction from B to A, which is negative 12 volts. It depends on which direction you're taking your measurements from. So in solving these equations, the positive and negative signs are important in front of where you're in front of both the number that you're doing and also from where you're taking them. And we're going to go through it again with a couple more problems in the future. So here we have current and voltage for different sources. So we are going to look at ideal sources early on, and then later on we're going to go through non-ideal sources. So for an ideal current source, that means you're only inputting current, and there's no voltage that comes with that. So the voltage stays constant across of it. So that's why in this blue line here we get a perfectly horizontal line. You're inputting, let's just say, 1 amp of current into your circuit. There's no voltage coming in with that, so you get a horizontal. So same thing with ideal voltage source. You're inputting 12 volts as a 12-volt source. You're going to get a perfectly horizontal line because no current is coming in with that. It is a perfect voltage a source. However, in real life, it doesn't really work that way. In real life, you're going to get some voltage coming with a current and some current coming with a voltage. And these are going to look like either lines that are have some kind of slope to them instead of a slope of 0 or a slope of infinity, or sometimes you get some even more interesting ones with curves and curvilinear lines showing different voltage to current capacities and voltage to current properties. But we're going to get into that a little more later. So another thing that we do in our circuits is we choose a reference or ground node. And so mathematically, it can work out that you can pull from many different places. I try to aim mine to always be on the negative side of whatever the power supply is. And I try to do it so it connects a couple together. Again, all these wires, the black wires, if you're looking at the top right picture, all of those are at the same, are essentially one giant blob of solder. So they have the same voltage at that set. So with that being said, it doesn't matter where you put your ground. The ground we call 0 ground. Actually, interesting story. Once upon a time, they used to plug like a large, either a pipe or whatnot, into the ground, literally, to make a nice 0, because that is a great place that you can deposit some of that extra energy. So lightning rods that go into the ground, they're grounding the house. And some of the times, for some of the early electrical engineering labs, they actually would take like a giant hole in the backyard and plop like a copper bathtub into it. And a copper bathtub is a great ground, especially if you run like a tube or a pipe from it. So if you ever asked in lab to ground something, if you don't have access to a proper grounding, sometimes a pipe can work, some that goes into the ground. Sometimes there's some other clever ways of doing grounding. But anyway, so we're looking at all potentials stated are relative to the ground terminal. So everything that we do here is relative to ground. So if you look at the bottom, the second drawing in the bottom, this is a totally correct but slightly weirder way of doing it, where somebody's put the reference voltage or the ground voltage of 0 in the middle of the at the top of the circuit coming out of the positive, and that's just going to flip all of your signs to be negative. So at your node 4, you're going to have a negative 6 volts in picture B, as opposed to a node 4 having a 0 volts in picture A. So generally, I'd rather keep everything, in my mind, in positive numbers if possible. So I try to always do a ground node coming off the negative of the battery or the power supply. Makes it a little easier in the future. However, just know, mathematically, if you want to do it a different place, you can do it. You're just going to start getting negative numbers out of it instead.